Good morning, everyone. Today we're going to be discussing part of Chapter 9. We're going to be doing the introduction to that, which looks at two primary number systems, rational and irrational numbers. We have technically seen these in the past. We've also just seen them this year too, though we haven't given them a formal name yet. So within rational numbers, there are multiple types that we can have. First and foremost, there are rational numbers themselves. These account for anything that can be written as a fraction. So for example, a half, well, this would be equal to 0.5. So this would be a fraction. We also have any decimal that ends. So for example, 0.15 is a rational number. It stops after 2 digits. The third option is any decimal that starts to repeat. So for example, 0.333, well, this repeats 3 over and over. Another option could be like 0.016, where the 16 is repeating. So this would be equal to, 0.016161616. So the only numbers that repeat are the 16. I have to keep making sure that the 16 repeats. So only the numbers underneath that bar repeat. So over here, this would be 0.333333333, just going on and on and on forever. We also know that a rational number is something that could be a whole number too. So like 2 is equal to 2 over 1. So this is a rational number. It can be shown as a fraction. So rational numbers also consider other number systems. So something that is a part of a rational number would be an integer. So rational numbers are like the most generic. So it's like a hierarchy of what counts the most numbers, and then our number of possibilities goes down and down and down. So integers are any number without a decimal that can be positive or negative. So -2 would also be like a rational number. -2 is an integer. -1 is an integer. 0 is an integer. 1 is an integer. 2 is an integer. And it keeps going up to infinity. That doesn't include infinity. Infinity is not a number. And it also goes down. So like -2 is 1, -3 would be an integer, -4 would be an integer, -5 would be an integer, so on and so forth. Then from integers, we have whole numbers. Whole numbers, if you think about it, you have to physically have something. Like to have a whole, you have to have something. So you can't have a negative for whole numbers. So whole numbers are just, well, I could have 0, that's part of a whole. So 0, 1, 2, 3, almost like the number of pieces you could have of like a cake. And then the last rational system are natural numbers. These we kind of view as things you can see in life and physically manipulate. So we have 1, 2, 3. It's really whole numbers except 0. And then it goes on. Now, an irrational number is something that cannot be represented as rational if it's not rational, it's irrational. So we've seen things like square root of 2. So can be written as a fraction of two integers, and this cannot be written as a fraction. So square root of 2, if I were to go plug square root of 2 into a calculator, so if I were to enter square root of 2, and then I look at the answer, so 1.414213562, well it doesn't repeat anywhere. There's no repetition to this decimal, so therefore it's an irrational number. 1.414213562. There are also some other important numbers in life that we use, maybe not in this class, but other places. So like in your calculator, you've seen the pi symbol. This is 3.14159. And it continues. If we were to go over to our calculator, there's also on your calculator the letter the lowercase e, that's also an irrational number. So if we go over to the calculator, we got second, here's pi. So it's 3.141592654. No, there's no repetition here. And then same with that second e. This is actually a good example of something that kind of looks like a rational number, because you could say, well, the 1828 is repeating because I get 1828. But this is where calculators sometimes give you rounding errors, or even they just don't go far enough. So like, sure, this starts repeating at the 1828 in this answer, but if I were to go further, I would find that this might be a rounding error here, or that it doesn't actually repeat this way. The next digit in this one is actually a 4, so that breaks everything that we would know about a rational number. So it wouldn't be repeating anymore. It would no longer be 1828. The next number would actually be a 4. So you do have to be careful sometimes with these. Generally, we're going to be giving you problems that are quickly recognizable, not something like E, where it's like, well, it looks like it repeats in a calculator, but in reality, that next digit doesn't. So you'll have more obvious things like square root of 2, or pi, or even, oops, I should actually write something inside for the square root, or even square root of 3. Well, square root of 3 is 1.7320. I don't see any repetition, really. This 0808 is going to stop repeating. Now, not all square roots, though, are irrational. Because remember, sometimes we can take the square root of a number, like the square root of 1 is just 1. Or the square root of 4 is 2. The square root of 9 is 3. So anything that's a perfect square within a square root is not an irrational number. So don't let that confuse you. Don't think, oh, well, just because one square root is means that they all are. That's not the case. Right. So I'll write a few more examples. So like the square root of 3 square root of 5, not all square root of a number are irrational. So like the square root of 4 is equal to 2, which is rational. We saw earlier square root, well, 2 is 2 over 1, and this is equal to the square root of 4 as well. Okay, so with that in mind, we can move on a little bit. So for exercise 1, we consider a number that is rational and one that is irrational. So the rational number is 2/3. The irrational number is a half. We have both of the numbers as less than 1. If we look at 2/3 in our calculator, 2 divided by 3, this is 0.66666666667. This last digit we can actually kind of ignore right now because we know that our calculator rounds the last digit. So this 7 is actually rounded up. If I were to do this out by hand, I'm going to quickly, so if I were to say do 2 divided by 3, well this goes in 0 times, then I have 20, so this is 0. Goes in 6, 3 times 6 is 18. I get 20 again, well this is going to give me a 6 again, so minus 18, so I'm going to get a 2 again, which means I'm going to get a 20 again. And I'm going to get another 6, so this is 18 again. So if you look, I keep doing the same exact thing. I keep getting 20, and I keep subtracting 18, which is 3 times 6. And the next step is going to be have another 20, and subtract another 18. It's going to keep going. It's going to keep giving me this repetitive decimal. So I'm going to write this as 0.6666 repeating. We notice it has a repeating decimal. .666 repeating would be the same as 0.6 repeating if you wanted to make this easier. But now, let's go look at the square root of a half. 1 divided by 2. Actually, I'm going to do this as. So if we wanted the half as the fraction, we would do alpha y1. This is 1. And then 2. Well, this is not really a nice number. There's no repetition to it. So I'm going to write 0.70. So if all these numbers are going to keep going and going, but it will never repeat. I'm not going to say never repeats, I'm going to say it doesn't repeat forever. Because there might be some repetition somewhere, but it's not continuous. It doesn't keep going forever. So in 2/3, we have some set amount of numbers that repeat forever. So like in this one, we had the 1/6 repeating forever. Here we just have 6 repeating forever. In this problem, we do not have something that repeats forever. Okay. We also have our second exercise. So in this one, we're going to be looking at more practice with using the calculator. So we want to write out every decimal your calculator gives you. for the irrational numbers. So let's start with, I think I already did square root of 2, did I not? I already got square root of 2, so 1.4121356. I think I copied that right. 1.412. So now let's look at square root of 10. Second, square root 10. So we have a 3, and then 16227766. Great. Okay. So sure, in this one I've got 2 and the 2 repeating. So you might, if you stopped here, you might think, oh, this is going to repeat again. Sure, you might think, oh, if I stopped it after the 7, it's going to repeat 7s. But every time I go a little bit further, I find that it doesn't actually keep repeating. So even here, it's not going to keep repeating the 6. It's going to switch. And then we can go check the square root of 23. So square root of 23 was 4.7958. Space that out a little too much. 3, 1, 5, 2, 3. So again, if we look at these, they go forever, and there's no pattern to the decimals. So they go forever, and no pattern. I have no way to tell you what the next number is going to be for sure. Sure, it might be a 3 again, but I don't know. I have no way to guarantee it. Okay. We do also note that the whole number keeps getting larger. So at square root of 2, our whole number, I shouldn't say the whole number was a 1. For square root of 10, the whole number was a 3. For square root of 23, the whole number was a 4. And this ties into the next part, which is that as we keep increasing, we can work with what we do know for perfect squares. So we know 2 is between the perfect squares. I'm going to write our perfect squares out real quick in order. 1, 4, 9, 16, 25, 36, 49, 7, so I have 64, 81, 100. Okay, so 1 squared is 4, 2 squared is, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared. So let's think about this. 2 is between 1 and 4, so it makes sense, or I should say the square root of 2 really. So square root of 2 is between 1 and 4, so the whole number, or the answer, is going to be between the numbers I would have to square to get there. So 1.414 is between 1 and 2. Here's square root of 2. Here's 1.4142 da, 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 da. The square root of 10 is between 9 and 16, and 3.162 is between 3 and 4. So here's B, here's B. Now square root of 23 is between this 16 and 25. And our answer, 4.79, is between 4 and 5. It's actually getting closer to 5, since 23 is closer to 25 than it is to 16. So here was C. So we can extend this idea to all of our irrational numbers. So without even using the calculator, we know 28, well that's between 25 and 36. So here's square. I'm going to do this in blue. So square root of 28 is closer to 25. Actually, I should be writing this not as the square root of 28, but just 28. So 28 is between 25 and 36. So therefore, well, to get to 25, you need 5 squared. To get to 36, you need 6 squared. So 28 is going to be between 5 and 6, or the square root of 28. Here's 5, then I'll have 5, then I'll have square root of 28, then I'll have 6. So this is between 5, 6, since 25 is less than or equal to square root of 28, less than or equal to 36. I'm going to make this a little bit further apart. Okay. Now, for B, we just need to go use our calculator. So we're going to switch over. I'm going to do second square root, 28, 5.2915062622. So we can copy that down, 5.2915022622. Okay, now for the simplest radical form, so part C, these are a little bit different. What we need to do is find factors of 28 that use perfect square. So in this case, if I go through the factors of 28, I have 1, 28, 2, 14, 3 doesn't work, 4 works, 4 and 7. I believe that is it. Okay, so 1, well 1's a perfect square, but that doesn't really help us, because then we have the same exact problem. This would be the square root of 1 times 28, which is, I can write square roots as, so if I had square root of a times b, I can rewrite this as square root. I'm going to actually move this over there. Now it's in the right spot. So the square root of a times b is equal to the square root of a times the square root of b. So the square root of 1 times 28, well this is the square root of 1, which is 1, times the square root of 28. This doesn't help us do much, we just get back to the square root of 28. That's not good. For here, well, 2 is not a perfect square, so that doesn't help. And 14 isn't a perfect square. That doesn't help. Our last one, 4 is a perfect square. So that's good. So this is equal to square root of 4 times the square root of 7. Well, what is the square root of 4? Well, to get to 4, I need to take 2 squared. So this is equal to 2 times the square root of 7. We're going to be doing more practices with those. But essentially every time you're looking for 2 factors, one of them should be a perfect square, and then you simply take the square root of the perfect square. So now, let's go on over, back to our calculator. We have to do 2 times the square root of 7. Oop. And if we look, here's the square root of 28, here's 2 times the square root of 7, and they're the same. Just looking at the 2 values in the calculator, there's no difference. They mean the same thing. Now I'm going to give us a few more practice examples that we'll run through quick. So if I had, sometimes these are a little tricky, the square root of 12, well, 12 can be 1 times 12, this won't matter, 2 times 6, or 3 times 4. 4 is a perfect square, so this is the square root of 3 times the square root of 4. Square root of 3, I can't really solve that, that's an irrational. I can't reduce it or simplify it, I should say. But square root of 4 is 2, so this is 2 square root of 3. Now let's say I had square root of 27. Well, 27 can be 1 times 27. It can be 3 times 9. And that's it. Well, 1 won't help. This will just give me back square root of 27. But 9, well, 9 is a perfect square. It's 3 squared. So this is equal to square root of 3 times the square root of 9, which is just equal to 3 square root of 3. So this is how we simplify radicals, is by writing it as a product of 2 radicals. And then once you have it written as a product of 2 radicals, if one of them is a perfect square, you can simplify it by getting the base of the perfect square. For some practice, I'd say look at square root of, how about 48? Let's do square root of 32. And square root of square root of 20. So try these on your own. If you have any questions, you can message me through Teams. Alright, have a good weekend.